All right, I have temporarily paused the event loop, so shall I restart very soon?
Yeah, go ahead.
All right, thank you. Well, in any case, so that was a bit of a false start, but welcome everyone to the very last tooling series workshop of this quarter. Today we'll be talking about regular expressions, also known as regexes or regexes, up to you how you want to pronounce it. But to start off, the links to the slides, the README, as well as some code we're going to look at later are here in these two links. If someone could send these links onto the chat, that would be great, because I can't really do it while my computer is set up like this. But yeah, and also if you have a membership portal account, then you can, as always, use this particular attendance code to gain credit for attending this event today. Yeah, cool, thank you. Thank you, Jamie and Christy. So my name is Timothy. I will be co-hosting this workshop with Christy today. She is also on the call, and she has helpfully sent something in the chat. So yeah, let's get started. So the agenda for today can be roughly divided into 4 parts. So first, we're going to talk about what exactly is a regular expression, and also like why does it exist, why do we use it, answering some basic questions like that. And after that, we'll have some mini exercises to test your understanding of the things we're going to be talking about in the very first section, as we wrote here. And then after that, which is going to be, so the first 2 parts are probably going to take a bit over an hour. The third part will be how do we actually make regular expression fast? So as we'll be talking about, one of the most important features of regular expressions is that they can be made very fast, even though they can be quite powerful. And here we'll take a slightly deeper dive into this particular section. And very last, we're gonna have some mysterious activities that we'll reveal later. Yep. So I guess to start off, let's provide some motivation for why regular expressions are used. So let's just say it's interview time, and in fact, hopefully, I just saw that that Elena just joined, and ICPC actually hosts these interview workshops that seem to be quite helpful. But today, I'm going to be specifically talking about one of these interview scenarios that you might see in a real life event. So you sit down in front of the interviewer, and the interviewer presents you with this particular problem that they want you to solve. So what they want you to do is to break a date of this particular format into its 3 parts: year, month, and day. So we see that so we're going to be presented with a string containing 8 characters. The first 4 are supposed to be year, represent the year. The next 2 are going to be a month, and the very last 2 will be corresponding to the day of this particular date. So yeah, so we have to write some code to split this up, and most of us have taken CS31 and 32, so we should be well aware of C++ and the string class and everything. So you know what, we've spent quite a while at UCLA, so we should be able to write something as basic as this. So you know what, so we just wrote something down. We call it parse date. We're taking a string, well, const reference to a string, but you know what, that's not the main focus here. And let's take a look at the strategy we use to implement this parse date function. So first of all, we're just gonna reject all the invalid dates really quickly by checking how long the date string we provided is. And because we know that the date has to have a specific format, which is 4 year digits, 2 month, and 2 date, we have to have the string being having a length of 8. And if we see that it does not have that, then we can just directly return null. There's some C++ technicality over here, but you know what, that's basically what's going on here. And after that, we can be reasonably certain that whatever we get is a valid date. And in that event, we will first create a date object, as we've done here. And then we're going to populate the 3 different fields of date, which is the year, month, and day, as we were requested. And so we use, let's just assume that we have a function called parse number that can basically look at some number in a string format and convert it to an integer, which is what we want. So we'll look at the very first part of the string, which is stir data. Stir data points to the very first character in the string. And we're going to say that, so here's where the year starts, and the year will take up 4 different characters. So yeah, that's basically what this part is saying. And then we are going to be looking at the next 2 digits, which are supposed to be the month. And in that case, we're going to say that, well, the first character corresponding to the month will be the 4th character, or actually the 5th character in the string. So the 5th character will be string data plus 4, because again, data is the first character. And if we add 4 to 1, then we're going to get a 5th character. Okay, that's great. And we also know that a month will take up 2 different characters. So that's what the 2 here is for. Okay, and then we are going to parse the very last component, which is a day. So it's pretty similar to what we just saw with month. We have stir data plus 6, because the day starts with the 7th character in the string. And then it's going to go on for 2 more, or for 2 characters. So that's the very last, we have 2. So not too much going on here, but it is important to note that we do some error handling at the very beginning. We check if the date has the correct size. But just for brevity, we're going to say that we're going to assume that the string we're given always contain valid numbers, and we're not going to get 13 as a month or 64 as a day or anything like that. So we're not checking the value of year, month, and day, just because that can get a bit more involved for our purpose here. Okay, so that's great, the interviewer says. But now let's also accept 2-digit years. And the reason why we want to do that is because in our particular organization, we have some legacy systems that still operate under the assumption that 2-digit years are okay. But we still gotta support these particular systems by accepting the date formats that these legacy systems happen to use. Here is basically the format of everything we're going to accept. So I use this parentheses to denote things that are considered to be optional. So because we know that we have to accept 4-digit years as well, but we now also need to support 2-digit years. So if we were to consider the things in parentheses, then we're going to get 4-digit years and then 2 months, 2 days. And otherwise, we're going to get 2 years, 2 months, 2 days. So we have to account for both of these possibilities. Okay, let's look at the code. Well, that wasn't too difficult because we just add some if statements and things will probably work out okay. So so a couple things changed. First, we see that str size, it used to be only checking for 8, but now we also have to accept 6 as a valid length of the string as well, just because we now accept years with two fewer digits. Okay, so that's this part right here. And we are also going to have some sort of Boolean variable right here that indicates if the year we're looking at is considered to be short. So the short year variable is going to be set to true whenever the string.size is equal to 6, because in that case we know that the date has to only have 2 digits for the year. Okay, then let's take a look at the other things. So here we're going to make use of the short year variable and say that so the year still starts at the very first character of the string, but in the case of short year, we should only look at the first 2 characters. That's why we have this little question mark syntax. If you haven't seen this type of syntax before, basically all it says is 2 if short year is true, or fall otherwise. So again, if we know that the year is 2 digits, then we just put a 2 here. Otherwise, we put a 4 there. Okay, great, awesome. And But because we change this part here, we have to adjust all the other cost to parse number as well. So here we have stir data plus short year question mark 2 and 4, because we know that in the short year format, the month actually starts at the 3rd digit rather than the 5th digit. But the 2 is still there because the month is still 2 digits. And similar thing for day as well. So it's going to be 4 and 6. So yeah, you can sort of figure out what these numbers are by just adding this 2 right here in the first argument to the 2 at the very bottom to result in the 4. In the case of a short year is true. And then you can add 4 and 2 together to get 6 in the other case. Okay, so we already see some complexity start creeping into our code. So here I use this question mark syntax, which is arguably a shorthand for just a full-blown if statement. So we have to use these tricks to make our code more concise. And also, just if you just look at this code, you see a bunch of numbers, and these numbers aren't really annotated, and they just seem to be flying out of nowhere. But if we sit down and try to figure out what this code is doing, then we know that what these numbers are supposed to represent. But you can think if we have too many of these, then the code is going to be, of course, pretty hard to understand for someone just starting out. Okay, great. And then the interviewer says, well, let's also accept the time. So not only are we going to accept all of those things that we just mentioned, having 2-digit years or 4-digit years, also month and day, but now we're also going to account for some optional time component as well. Okay, so well, first of all, the initial length check here is going to be a lot more complicated, because not only do we have the possibility where we have a 2-digit year or 4-digit year, we also have those possibilities plus additional characters on top of that. So if you look at the particular time format we're given, so we have 2-digit for the hour and 2-digit for the minute, as well as a space before the time, as well as a colon between the hour and the minute. So that would be six characters in total. So we have to accept 12 as a possible length, as well as 14 as a possible length. So I got that just by adding 6 to 6 and 8 respectively. The short year variable is also going to get a little bit complicated. So not only do we know that 6 is a short year case, we also know that 12 also has a short year, because 12 is again 6 plus 6. So we get the date component, as well as the time component. Okay. Fortunately for us, the year, month, and day components don't really change, because these things don't really get impacted just by adding a time component at the end. But we also have this if statement right here that says if the size is either 12 or 14. So in these two cases, we know that there is a time component in the string. And in these cases, we're going to consider the hour and minute things as well. Okay, so yeah, more magic numbers, 7, 9, where do these things even come from? I have to sort of use my fingers and stuff to try to figure out how many characters is actually supposed to be the hour. So it turns out to be 2 days plus a single space. So yes, 7 is correct. But then you also have the colon, so 7 plus 3 is 10, 9 plus 12 is 9 plus 3 is 12, etc. So still seems to work, but getting more and more complicated by the minute. Okay, and now the person says, okay, we have to also accept the time zone. And why? Because we are an international company. We have offices around the world. We have offices in Mumbai, in London, in Paris, in Santiago de Chile. We have offices in all of these places, and we really have to coordinate our events for these different offices. So we're going to add a time zone, and the format of time zone is pretty standard. So it's going to start with UTC, like the 3 literal letters. It means universal something time coordinated, something like that. But it just says time in London, basically. And then we are also going to have either a plus 2 digits or minus 2 digits depending on if you're west of London or east of London. Okay, so there's this part right here. But we also have this little 30 component that's possible. And why do we have this? It's because in some regions, like in India, the time zone is actually like a half hour ahead of London, for example. So we have an office in Mumbai, as I mentioned, so we have to account for Indian Standard Time as well. So that's why you have a 30 component right here. Okay, so a bit more complicated, and yeah. So, but we know that the time zone component can only appear if the time component is there in the first place, because it doesn't really make much sense for us to have time zone but no time. So that's something we notice. Okay, so we're gonna buckle down and actually do this thing. Okay, much more complicated. First, now we see that there's 7 possibilities of the string size that we have to consider. Why 7? Because it just happens to be a case that if you add whatever number of letters to 12, it gives you 17 and 21. If you add a number to 14, it gives you 21 and 23. So there's actually a little overlap here. The 21 is an overlap case for both 12 and 14. The short year check is going to be a bit odd. What's going on here? It's going to be a bit bizarre. So we're going to actually check if the 7th character within string is the empty space, just because we can't really use a string length based check anymore, because we know that it could either be that we have a short year, or it could be that we just have like a 30 component at the end, like again India. So yeah, we use this particular check right here. In fact, yeah. So this, we're gonna have to do this. Now you might wonder, wait, is there even a 7th character? Well, in fact, we know that in this case, in the stir size equals 2 case, it's not even there isn't even actually a 7th character, but the 7th character is actually null. So this isn't going to lead to a crash, but it doesn't actually work. Okay, so that's a bug in my program, but sort of illustrates my point of this getting more and more complicated. But anyway, so the year, month, and days part still stay the same, thankfully. And then the string size check for the hour and minute component is now going to be a greater than or equal to sign. And we're going to use 12 right there. So yeah, more magic numbers. Hours and minutes are the same. Okay, great. So size 19. So this is going to check for the time zone. And we know that the possibilities with the time zone are only going to be 19, 21, and 23. So I think this check is fine right here. Okay, so we do a bit more stuff. We have to mentally calculate the index for the time zone. Apparently it's 16, 18. And we're also going to consider the case of having a half time zone. Yeah, and I'd also like to take the opportunity to point out that some places actually have like 15 minutes ahead of the standard time zone, but our code is only going to handle the 30 case because this is getting long enough already. But anyway, so yeah, so this is pretty bad, huh? Yeah, even looking at it now, I can figure out some bugs. Like, for example, if the time zone is negative, then we actually have to subtract 0.5 from the time zone. But so this part wouldn't even work. So yeah, I wrote this code. I looked at it a few times. I discussed with other people, and still we were not able to find all these bugs in the code. So so yeah, this is pretty bad already. But at least we have something down on the paper, which is always important in interview, or so I heard. But you know what? So this code right now is pretty like we can't really understand it just by looking at it, at a first glance. So yeah, well, thank you, Jamie. That's a very useful addition. But that's what you would do if you want to actually make this code semi-work. But if we were to try to extend this thing anymore, I don't know if we're going to be able to do this. So you know what? We're just going to turn this code in and hope that this is the very last task we'll be faced with. Okay, the interview says, let's also accept seconds. And by this point, I really have no other choice than to say, give up. We give up. We we can't do this anymore. It's getting too complicated. We don't even know if the code we wrote works. Testing it will take too long, and we have to accompany like some factorial number of test cases to actually make sure this thing works. So yeah, this is pretty bad, and it's probably reliable to assume that we did not get the job and hence not stunks. Yeah, so that's sad. But consider the alternative universe where the interviewee actually knew about regular expressions and how to use regular expressions. And let's just take a few snippets at this alternative universe and see how things will work out so much better. So the very first task for us is to break a string into 3 pieces specifically. And this piece of thing right here, let me count how many characters it is. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this 9 characters really does basically the entirety of that very first task right there. So there are a few parts right here. So there's bracket 0 through 9, which basically says we're going to be looking for a digit that could be anything between 0 and 9. And then we're going to have this braces with an 8 in it, which essentially signify that whatever we have before it, we're going to have 8 copies of it. So so this thing basically says we're going to have 8 digits, which is a lot more than what we did earlier. So as I mentioned, we didn't even check if the numbers were actually numbers. We just assumed that they were numbers because it will take too long to actually check if it's true. Okay, but I hear some of you complaining. This is great. It checks a lot of things, but it doesn't actually do what the interviewer asked. In particular, it doesn't actually break the string into 3 pieces. It just checks if everything is a digit. Okay, well, that's fair. Let's fix that. So this thing looks slightly more complicated, but in reality, it's really not. So the first change we see, and the most obvious one, is that we have a bunch of these question mark then angle brackets things. And this is basically just a way for us to group things and give them a particular name. So so first of all, we have the year component. We also have the month and day components, just listed out right here. We also replaced the 0-9 within brackets to this alternative representation, which is \d, which stands for digit. But in fact, these 2 things are completely equivalent, and I'm just going to use \d from now on, just because it's shorter type. Okay, so so first we see the year has 4 digits, the month has 2 digits, and the day has 2 digits. Okay, so and this is still a lot simpler than what we saw earlier in the handwritten C++ code, but it works. You can't really say it doesn't work because it works. So yeah, so much simpler. But the real power comes in the extensibility actually. So to allow for 2-digit years, all we have to do is to find the first 2 digits and surround them with quotation marks and put another question mark right after it. And in this context, the question mark means optional. So we're going to accept both years with only 2 digits, as well as years with 4 digits, which is the case where we add these, we account for the things within the parentheses right here. Note that even though we saw the question mark earlier in the angle bracket syntax right here, these are actually different. And it's easy to tell which question mark means what. If you see that there's things before the question mark, which is the case here, we see that there's a parentheses with 2 digits in it. So in this case, we know that it's optional. But in other cases where we see that there's a question mark right after a parenthesis, then we know that there isn't anything to be the optional of. So so here we will actually just be giving a label to whatever we see. Okay, and if you look at this, it's literally so simple. We just literally split the \d brace 4 into 4 \ds and put a question mark after 2 of them. I mean, like we didn't have to do any like Boolean variables, is short year, weird length check. We didn't have to do any of those. Everything is actually automatically done for us. Okay, and now the task is for us to add time support as well. What we see here is that the first part is actually identical. Like the year, month, day part were identical. All we had to do was to add these two more things, the hour and minute things right here, which are things that we've seen before. Hour is pretty much identical to day, and so is minute. And these two things are all surrounded by a pair of parentheses, which means that these two things should be taken as a unit. And we're going to say this whole unit is optional by putting a question mark at the end. We also have a little colon here and a space here to denote that the time has to come after the date, separated by a space, and the hour and minute components are separated by a colon. Okay, and now the real challenge comes, which is the thing that really made everything a lot more complicated, and that's the time zone component. So again, we don't really see changes to any other parts of the code. All we had to do was to add this UTC thing to right after right next to the minute component. So we're going to say UTC, okay, and then we're going to have this thing surrounded by parentheses that we call the time zone. And within the time zone, we're going to say bracket 0 plus minus. And again, bracket basically means anything within the brackets are going to be acceptable. And we know that there are places east of London as well as west of London, so we accept both plus and minus. We also have \d, which are the first two digits within the time zone, as well as two more of these with a question mark specified as well. So this accounts for the fractional time zone, as I talked about earlier. So yeah, so this and UTC as well as time zone component are surrounded in more parentheses with a question mark after it. So this basically says that the time zone is optional, and this whole thing is surrounded by another parentheses, which signifies that the whole time component is optional. Yeah, it's incredibly elegant, as I see some of you have noted. But so I don't think I have an example for seconds, but I mean it's very easy to actually just put a second component here and put a question mark after it. So I see a question right here. So is this regular expression thing in place of a function, or do you put this inside some function? So you can definitely put this inside some function, but at some point, it's going to be so easy to use regular expression to match for things that you don't even need to put in a function anymore. You can actually just say, date regular expression dot match string. So you don't even have to have a parse date function anymore. You can just use this thing directly. But we'll also see that regular expressions have more uses than just in programming. In fact, we're going to have some additional examples of using regular expressions elsewhere. And in those cases, we don't really have the question of do we put this in a function or not, because it applies in more than just programming itself. Hope that answered the question. Yeah. Okay. So what lessons do we see here? So not only is regular expressions a lot shorter than the equivalent C++ code, we also see that it's quite flexible in that we can modify parts of a regular expression without having to change anything else in the regular expression. The main thing that really made our code a lot more complicated is that when we add more features into our code, we have to constantly look back at the length check, for example, or for other things to make sure that they still work once the new string format is added. But here, we don't really have to do any of those. We just add more code and things magically work, which is really how computers are supposed to be. Yeah. So let's having done that grand introduction of regular expressions, let's give a more formal definition of what regular expressions are. So one way to explain what regular expressions are is that they are basically patterns that you can tell computers, which allow the computer to do quick and easy string matching. So in actuality, the regular expression is basically just a way to tell the computer what, like, we're looking for a string of a particular format, and you or the computer will now have to try to use this pattern to try to match the string that we're given. And in the previous case, we saw that we use a pre-composed pattern to try to match for date strings, but really they are quite flexible and you can find them everywhere. So on the left-hand side right here, we see that there's a use regular expression option as part of the search toolbar inside Visual Studio Code. So this whole thing is Microsoft Visual Studio Code text editor, and you can easily enable regular expressions within part of this just by clicking on this dot star. On the right-hand side, we see something that's completely not programming related. So this is Firefox, and I just recently downloaded a Firefox add-on called Find It that basically allows me to specify regular expression to search for things on the page, on the web page, that is. So here I have \d, then braces 2, which basically just says look for 2 consecutive digits. And once I hit enter, it's just going to highlight all of these instances of consecutive digits to me. Here I have 1 0 being highlighted, 1 1, 1 2, etc. But just only 1 doesn't actually satisfy the pattern we specified. So yeah, so this is super useful if you're trying to look for a list, like a list of words in a page, for example. If you have to search them separately, then sometimes you might lose track of the position of the previous match, and etc. So you can think of quite a few different use cases for these things. Just as a matter of history, regular expressions were really initially popularized by Unix tools. So if you have taken classes like Computer Science 35L or 97, you talk about tools like grep, which searches for a pattern within your file system. So look for files with a particular regular expression pattern, as well as sed, which can actually not only match for things but also replace things using the patterns that you specified. So you can say things like replace the third D on the line with an E or something like that. And again, regular expressions are also available in most programming languages. In languages like C, you don't really have regular expressions built in, but you can always find libraries that implement it for you. But in newer and say more modern languages, like say JavaScript, Python, maybe even C++, I'm not sure, you can actually just use regular expressions because it's built into the language itself. So it's quite convenient without having to download any additional packages and stuff. And even in C, I believe you can just directly use regular expressions that's implemented in part of the operating systems. But I believe this only works if you're on a Unix-like system, like say Mac OS or Linux. I don't think Windows provides that functionality. So we've already seen some of the regular expression like syntax earlier, but I'm just going to dump all of these syntax in one slide so that you have a place to reference to. So if we just put an A in a regular expression, then this regular expression is gonna match the letter A, which is pretty intuitive. But there's also like a more advanced version of matching for a letter, which is a dot, which matches for any letter. Actually not just any letter, but also any characters. So numbers, symbols, all of those things will work as well. So if I put, like, for example, B.B, then it's going to match for things that have B's on either side of it. So for example, it's gonna, I can't really think of words that says B Anyway, let's try a different example. B dot D. In that case, this regular expression will actually match bad as well as bed. Maybe bod too. I don't know if it's a word or not, but aha, bid. Thank you, Jamie. Bid and bud. So all of these words will actually work for this particular regular expression that I just made up. There are also these things called anchors. So there's the caret, which is on top of the 6 on most keyboards, as well as the $sign. So what these anchors do is that they match for the beginning and end of line. So if I say, for example, caret A, then it's going to match for A's, but only if they occur at the beginning of a line or the string that we provide to the regular expression. Okay, so all of these things are sort of individual things, but and then let's take a look at some of the more, say, useful things that that regular expression provides. So here we have A star, which says matches 0 or more letters A. So it's not only going to match the empty string, but also a single A, 2 A's, 3 A's, 4 A's, all the way until infinity, or as much as your computer can handle. So yeah, so if I were to say replace, maybe not. Maybe we'll do an example later. But one of the more useful combinations of regular expressions you'll see is if you combine this asterisk with the dot we saw earlier. So dot star basically means match anything, match the entire string. We don't really care what's in the string, but we're going to match all of it. That's essentially what it says. And in fact, it's used so often that that you see this dot star thing as sort of a symbol for regular expressions. So if I were to be allowed to go back a few slides to right here, we see that in regular expressions, or in Visual Studio Code, we see that they use dot star as a symbol for regular expressions. And not only do you see it here, you'll see it elsewhere as well. Okay, so that's star. A plus means 1 or more A. So it's not going to match the empty string, but it is going to match 1 or more. So A works, AA works, but not the empty string. And you can think of a few cases where this can be useful as well. For example, if you want to look for, I don't know, 2 consecutive spaces in your source code for whatever reason, then you can use this regular expression. And you can also combine these things together. So you can do, for example, A plus then H, then it's going to look for all combinations of ah in your document. So AH works, AAAH works, AAA, infinity A's, H also works. So you can, aha, thank you, Jamie. So yeah, that works. We also have another one, the question mark that we already saw earlier. So I sort of informally introduced it as optional, but more technically, we can characterize it as 0 or 1. So we are going to have either none of this, like the empty string, or we're going to have one of these. In fact, you can combine this question mark with other things as well. So we saw earlier that if we use a parentheses, then we can group things together. And having a question mark after the right parenthesis will give us basically an optional, like that whole thing as a unit. We also saw the braces syntax earlier. So A brace N will give us something that matches N A's. But we also have a slightly more advanced version. So if we put a comma and then M right after it, then we're going to match between N or M occurrences of A. This is sort of pedantic, but you can also just say N comma, in which case it'll be at least N A's. Yeah. We also saw brackets earlier. So basically this is matching for one character that can be any of the things that we specify within the brackets. One of the useful features that we can use here is a dash syntax, basically saying that we can match not only A and Z, but also everything in between. So A, B, C, D, E, F, G, all the way until Z. So So this particular example we have here matches the lowercase letter or 1 or 2 or 3. We have 2 more to go. So the type, which is a letter you should usually see beneath your backspace. So this particular thing says or. So we're going to match ABC or DEF, but not both. So if we were to give it ABCDEF, then it's only going to match ABC and DEF separately. It won't match the whole thing. I know that sounds sort of weird, but trust me, there are applications for it. And yeah, finally, we also talked about the parentheses earlier, which groups things into a unit. So if I were to say AF, and then within it, it's BC or DE, then it's going to say ABCF or ADEF. So that's what the parentheses does. So yeah, I just went through like, what is this, 10 of these? You know, there are actually more things regular expressions, but these are definitely the most useful that we're gonna see. And I also just want to say that you don't have to memorize these things like specifically, just because, you know, there are a lot of these, and I've always found that using these things through experience helps you learn these things a lot better than just trying to memorize them just like directly. So so even if you forget, always feel free to come back to the slide or to our README, which has I believe a near copy of this, or even just like look up regular expression cheat sheet on the internet, and you're going to be met with so many different resources on regular expressions. So yeah, so this was just meant to be an overview. No need to actually, you know, try to memorize all these things right now. So one more thing before we get to the mini exercises is something I want to talk about, which is the different flavors of regular expressions. So regular expressions are actually really old. They've, you know, being invented, you know, right after World War II, actually. So they've really had a long history, not only in computer science, but also in other sciences like linguistics, for example. So it should come as no surprise that we're going to see different variants of regular expressions that have different features and different characteristics. So the first one we're going to see is the POSIX flavor. And in particular, POSIX actually specifies 2 different flavors, even sub-flavors, if you will. So there's a basic regular expressions, or BRE, and extended regular expressions, which is called ERE. So this type of regular expression is found in, you know, the old Unix tools that I just mentioned, like grep sed, and also VI, or its modern incarnation called Vim. And it's also found in certain languages like Go and Rust. So so these are old. They are slightly restricted in terms of features, but they execute very fast. And I'll mention how they make it fast later. And the other major variant is what I'll call the Perl-inspired regular expressions. So, and what they do is that they provide more features, like, for example, look-aheads, or matching the same string multiple places, or look-behinds, and, you know, and other similar things. So yeah, more advanced features, but slower. And this type of regular expression is found in a lot of the more modern languages, like say Perl, Python, JavaScript. It's also embedded in other tools like grep, which has a Perl mode these days. And in grep, the Perl mode is actually backed by a library called PCRE, or Perl compatible regular expressions. So yeah, so if you want to you know, create a new C application and want to embed the Perl-like regular expression into that application, then you can just go install this library and make it automatically work. So yeah, and with this, I will turn the stage over to Christy, and you guys will be able to do some practices for regular expressions. Christy, do you want to take over?
Yeah, I'll share my screen. Thanks, Tim.
Yep.
All right, so if you go to this link, regexer.com, we're going to be using this to practice writing regular expressions. And then the exercises that we'll be doing, I'm going to put both of these links in the chat. Where's the chat? Oh, here. And then the exercises we'll be doing is in the second link, the tiny URL, which will link to a README, or not a README, sorry, a Markdown file. So the way this is going to work is that there'll be a section. So we'll have 3 sections, and between each section, we're going to go over the answers. So first we have street addresses. Each one corresponds to a particular situation. It gives you some instructions. For example, match any instance of road that can be replaced with road. So what you want is you want to copy over this text into the regular expression tester. And then write a regular expression up here that matches what the instructions say. So for example, for street addresses, you want to match these 2 roads. So you can imagine a situation where you might want to do this. Let's say you're like processing a bunch of addresses and you only want the last part road. But if you search just ROAD, road, sometimes you'll get roads that you don't want. For example, the road inside Broad Road. So the goal of this exercise is to write an expression such that you highlight only the last road. Some things to note about this is that if you decide to use the start and end of string, so that is the caret, that is the caret for start of string or dollar for end of string. If you decide to use that in your expression, you want to make sure multi-line, which is under flags, multi-line, is highlighted. Otherwise, you may have unexpected results. And yeah, so I'm going to give a few minutes for the exercise. If you have any questions, just drop it in the chat, and then we will review in a few minutes, let's say in 5 minutes. Oh, and just a note about Regexer is that it uses the Perl-inspired regular expressions that we talked about a little earlier. All right, so now it's 6:55. Hopefully you had a chance to complete that one. We'll now go over how you might approach it. So there's definitely a ton of different answers you can get. Not like the one that is correct, like correct in quotes, is the one that works for whatever actual situation that you're using it for. Oh, so I already copied this one over. So one way you can get just the last road is to add this $sign, and then you have road and road. Another simple way to do this, even though you have the extra space, is just put a space before road, and then you'll only match this road. Another fancier thing you can do is use this /b, which means word boundary, and you can put it at the front, and similarly at the end. So those are a few different ways you can solve this one. So for our next section is on phone numbers. So you can imagine trying to find phone numbers in this format, and also maybe you want to extract the area code from it. So in this situation, just copy this over. You want your expression to only highlight the valid phone numbers. So any phone number that has 3 digits, a dash, 3 digits, and then 4 digits. So you should highlight like this. And then in the second part of phone numbers, you want to match the same phone numbers with the dash, as well as phone numbers without a dash. So any phone number that has 369, that has 10 numbers. And then for the next section, you also want to try to match with an area code in parentheses, either without a space or with a space. So this one is harder than the previous exercise, but we'll also give it 5 minutes. Oh yeah, and this is important to note for the last section. If you have parentheses in your expression, you'll want to use the backslash to escape it. Otherwise, it'll think it's a special, like regular expression syntax character. And this is true for any special character. For example, the dot, since the dot means any character, if you want it to actually mean the period, you want to escape it. And even the backslash needs to be escaped. So go ahead and try this one. We'll review at 7:05. All right, so it's 7:05. Let's go over how to solve this one. I'm going to copy over the first version. So I want the dash format. Oh, I already copied it over. So I can express it as 3 numbers, a dash, 3 numbers, and then 4 numbers. So dash \d matches any digit character. So you'll notice that if I just have this, each digit will be highlighted. And I want to say 3. So this represents the first part. Then I have a dash, so 3 digits and a dash, another 3 digits, and a dash, and then lastly 4 digits. So that will match the first expression. Next, I want all the previous phone numbers, and also maybe there's not the dash. So I will make the phone number, the dash is optional with the question mark. And then you'll notice also this partial line is matched. So I might want to, like, depending on my use, I might want to only match ones on an individual line. So that means only matching start of string, end of string. And make sure for this that the multi-line flag is enabled. And then you'll notice that's not highlighting anymore. You'll also notice that this allows like only one dash, which this format doesn't like look that nice to look at, but maybe depending on your use case, maybe you would also write an expression that does not allow this one. But maybe in another use case, it's like totally fine. Lastly, this is the area code in parentheses. So I'm going to use the OR operator. So that was the single bar. So one possibility for the single bar, I'm going to say, is the is what we originally had, which is just 3 digits. And the other possibility I'm going to say is 3 digits, but in parentheses. So I'm going to write these 3 digits, and then remember that parentheses need to be escaped. And like a nice thing about this website is that it highlights things differently. So escape characters are pink. And then lastly, if I want to allow the space as well, I'm going to do an optional space. So I'm going to put a space and then the question mark to make it optional. And then that should match all of these phone numbers. So our last exercise is definitely the hardest, is matching any valid Roman numeral. So you've probably seen some Roman numerals before, like I, IV, and they correspond to these numbers. For example, I is a 1, and then V is a 5. And the way Roman numerals are built up is that they have different place values and then different ways of expressing each place value. So for example, the Roman numeral XCIX can be broken up into 0 for the thousands place, 0 for the hundreds place, XC means 90, and then IX means 9. So then XCIX means 99. And so in this exercise, it's broken up into different parts that match each place value of a Roman numeral. And the very last one is to match any valid Roman numeral. So for example, the first one, there's 3 possible valid thousands place, M, MM, and MMM. And also empty string. Empty string is not written here, but that is also a valid thousands place. And then, but 4 M's is invalid. And this is not really necessary for the regex part, but it's like nice to know that M means 1000 MM means 2000 and MMM means 3000. And similarly, these are the possible hundreds place for a Roman numeral. So C is for 100, CC is 200, CCC is 300, CD is 400, and so on up to 900, which is all the possible hundreds places. And these are not valid hundreds places. The same thing is for the tens place and also the ones place. And then finally, you concatenate all of the places together, and then you should be able to see which Roman numerals are valid and invalid. So the last one should highlight with these as valid Roman numerals and these as invalid Roman numerals. So we will review this one at 7:15, that's like too little time, I think. Let's do let's just do 7:20. All right, let's review the Roman numeral section. So first, we have the thousands place. So this means we want either 0, 1, 2, or 3 m's. So let's write the expression here. So m 0 through 3. And you'll notice here, like I highlight invalid because it matches the first 3 and then 1. If I only want to match single lines, I can change it to have these. All right, that one is the easiest one of these. Next, we have the hundreds place. So we're going to start off the same way as the thousands place with this section. So it's exactly the same except the letter is C instead of M. And then we highlight those. And then we can notice that this section is also basically the same except there's a D in front. So if I want to match that, then I put a D. And then this part is 0 to 3. So that's why this one is also matched. But if I want to match both, then I can make this D optional. So match 0 or 1 Ds. And then we have these sections highlighted. And then lastly, I'm going to highlight the last 2 sections with the or again. So we can also allow CD or CM. And this will highlight any hundredths place. So these are all the valid hundredths place in Roman numerals. Next, we have the tens place. So if you notice in the tens place, it's actually the same exact pattern as a hundreds place, except C is replaced by X, L is replaced by D, or I mean, yeah, D is replaced by L, and one more, something like that. So I'm just going to replace these. So it's the same expression, except that instead of C, we have X. So it'll match these 3 X's. Instead of D, we have L. And then instead of CM and CD, we have XC and XL. So that will match any valid tens place. And then the last one is the ones place, which is also exactly the same, except that the X's are now I's, the L's are now V's, and then we have IV and IX. And then lastly, we put it all together to match every single valid Roman numeral there is in a single regular expression. Isn't that wild? Okay, so first our ones place is already matched. I'm going to add the tens place. So again, that is any, so we have the 3 X's, we have the L's, the optional L, and then we have the XL and XC. So now that matches, well, okay, all of these have thousands place, so we're not gonna match anything invalid yet. And then we have the hundreds place. So instead of X, we have C, instead of L, we have T, and instead of CM and CD. So that'll match any hundreds place. And lastly, we have the thousands place, which is 0 to 3 M's. And there we have it. We match every single valid Roman numeral that exists in one expression, this expression. Yeah. So next we have Tim with the theory.
Thank you, Christy. Let me share my screen. Can you all hear me?
Yes.
Thank you. Let's see. Okay. So yeah, thanks again to Christy for doing some of the mini exercises that we have. Um, so yeah, so for the second half, I would like to focus a bit more, not less on the using regular expression side, but more about how you actually make regular expressions work. Um, so I just want to preface this whole discussion on the theoretical foundations of regular expressions by saying that the regular expressions things are really one of the crowning achievements of computer science. So yeah, so people discovered back in the 60s or the 50s that every regular expression can be implemented in what we call linear time. So basically, this means that regular expressions can be very fast. If you have say n characters to try to look through, then every regular expression can run through that string in a factor of n times. And this is despite the fact that regular expressions can be quite powerful, as we've just seen, not only in my motivating example, but also in some of the examples you all did with Christie's mini exercises. How do people actually make this so fast? So what happens is these regular expressions things will be transformed or converted into an equivalent finite state automaton. So fancy word, like what's finite, what's state, what's automaton? Well, so for now, we're not going to worry about these specific terms, but we will look at how or FSAs will actually work for regular expressions. So very simply, FSAs or regular state automata are basically mazes. And along with the maze, we also have a mouse and some cheese. So basically, the whole thing can be seen as a game. So a mouse is dropped into a maze at one of the starting points. And here we see that the Q location has an arrow pointing to it, but the other end of arrow is empty. So this is our way of saying that this place is where the maze should start. And the mouse is, of course, right here. So it's at the starting state. But we also have cheese at some other locations that are marked with 2 circles. And the goal of the mouse is to find the cheese or to access the cheese somehow eventually. But there's a twist to it. There's a twist to it. And it is in fact that some paths or these arrows things have tolls. So to get through some paths like this one right here, the mouse has to give out one of its most prized possessions, which is a computer character. So this arrow that's marked with an A basically says, hey, you can get through me, you can get past me, but only if you give me an A in return. But if you only have a B, then you will not be able to get through this path to get to the cheese. And if you think about it, if you squint at it hard enough, then you can see that this is in fact the regular expression A. So the mouse can only pass through this if it has an A. So and a different way of saying it is that we can only get a match for the regular expression if we can provide an A. So yeah, so you can let's do a few more examples on how we can convert other things into this type of maze setup that we have here. But before that, some paths are freeways. So these arrows that have not a letter or any other character, but this weird epsilon thing are called epsilon moves. And these things are free, so the mouse can go through it without having to give out any of its characters. And in this case, the mouse starting at Q can just directly go to F and get the cheese. So this particular finite state automaton wouldn't be super useful just as a regular expression, because very rarely do you want to actually match, nothing. So yeah, so that's pretty useful. We're going to see that these epsilon moves can be quite useful in making other parts of regular expressions work. So that's why I want to just introduce it just at first, so that you guys won't be surprised when we see something like this. Okay, so once we know about this, we can then take a look at having two things together. So let's think about the regular expression AB. So what we really want to do here is that we want to first look for an A, and right after that, we need to look for a B. So for the mouse to get through the entire maze to the cheese, it has to first pass through this very first arrow, which has an A. So by doing that, it gives out an A character. And then after that, we also need a B to actually get to the final destination. So this whole thing seems to work quite beautifully, but there is like one additional twist, and it is that you have to give out like whatever character you try to give out. It has to be the very first one you have. So if the mouse has B and A, it wouldn't actually go through this path because A is not the very first character it has. So yeah, BA wouldn't work, but AB in that particular order would in fact match the regular expression and also allow the mouse to get to the end. One more thing to note here is that I use this little slash syntax that we also saw earlier in regexer to denote the start and end of a regular expression. Yeah. So in this analogy, ABC will work, right? So yes, ABC would work because we don't really have a $sign at the end. But if we do have a $sign at the end of the regular expression, then we are fixing or anchoring this regular expression to the end of the string, and it wouldn't work. So yeah, so we're not really thinking too hard about where the match starts or where the match ends. So you can even think the mouse can throw away an arbitrary number of characters first before entering the maze. So and that will allow us to match use the regular expression to match any part of the string that starts after the very first character. Okay, and of course the mouse complains about taxes because now it has to pay 2 characters rather than just 1. Yeah, that's just the little analogy I have. Okay, so we talked about A and B, but we also have A or B. And how do we actually do that? So so here's how it works. It looks a bit complicated, but let's take the role of the mouse and try to walk through this maze together. So here we have the regular expression A or B, so A pipe B. But it's just really the same thing as brackets AB. So these two things are really identical and equivalent regular expressions. So we start off with this little starting state that we label as Q. By state, we also mean location. So each one of these circles is a state / location. And once we get here, so we are going to pick a path to take. And these two things are both epsilon moves, so we actually have to look past this one arrow into the next arrow to see which path to take. So in particular, if the mouse has an A, then it's we're going to assume that it's very smart and looks into the things that are going to come next and go to the very first path. Otherwise, if it has a B, then it's going to go to a second path, and if it has a one of the other characters, then it won't be able to get to the destination. But once it pays the A tax or the B tax respectively, it's going to get through to the next circle, and the next circle really has a freeway on to the very final state that we have to look at. So because we have an epsilon move right here. Yeah, so we can think we can sort of see how this works, right? And we can't really think of any counterexamples where this thing wouldn't work. So now is a challenge for you guys. So we've talked about these two things, and ors, but what about question marks? So if we have the a question mark regular expression, how can we actually convert it to a maze that the mouse can get through? And my hint to you guys would be to look at the previous maze that we have here and try to modify it in some way so that we can implement the a question mark finite state automata. And yeah, if any of you guys have any ideas, please feel free to jump in the chat or even try to unmute yourself. Yeah, and please let me know if you want to talk, but for some reason are unable to unmute. Any ideas? So yeah, again, my hint is to look at this and try to change it somehow so that we can make the A optional rather than making it A or B. So so Tim mentioned that what we can do is to somehow add a shortcut for the mouse. So instead of making the mouse go through this, this entire path to try to get to the destination, we can sort of just, provide a direct shortcut through that bypasses all of this, all of this stuff. So yeah, that totally works. And in fact, we're going to take a slightly more progressive path and say that so the only thing we have to do to change this thing to be a question mark is to change the B right here to be an epsilon. So if we look at something like this, then we know that if we don't have an A, then we can just go to the first path and it's freeway all along, and we can just get directly from Q to F without having to think about anything else. But if we do have an A, then it can go through the second path, which requires an A for us to go through it. So yeah, this totally works. And I also like to just note that a question mark can really be rewritten as a pipe than nothing. And in that case, we can literally use this particular translation to mazes that we talked about for the OR construction. Yeah, so this is one way, but we also see that there are a lot of these epsilons things flying around, and really it seems to be much ado about nothing. From Q to F, we have to go through 3 arrows to get there, even though epsilons don't actually do anything to our maze right here. So what we can do is actually to simplify it just a bit. So in fact, it can be simplified as far as to this. So we say that we can either provide an A when we get to F from Q, or we can just not do anything, just not provide any output from when we go from Q to F. So this is in fact totally equivalent to what we saw earlier, except that we just remove the epsilon paths to be empty. Yeah, so some of you may have the question, how do we get rid of this epsilon as well? So that's a bit more interesting. But one way we can do that is actually to put some cheese at Q as well. And that will get rid of the epsilon path. So if we have an A, we can go from Q to F where there's some cheese at F. But if we don't have an A, then we can just stay at Q. But again, this gets into a question of like, what if the mouse gets lazy? What if the mouse just wants to stay at Q even though it has an A? And this is where the analogy sort of falls apart a bit. But you can just think of it as that like we are forcing the mouse to be as diligent as possible when looking for paths to the very end. Yeah, so in other words, we are forcing the mouse to be eager rather than lazy, using more computer science-y terms. Yeah, so that's question mark. But we also saw other things earlier, like say the repetition operator, like the asterisk. So so the way we can handle those cases is by adding these self loops. So for example, if we have the regular expression a asterisk and b, then we can start out with a q location, and then we put a self loop through q with an a marked. So this basically succeeds in doing the following. We're going to get through all the a's we have, and then we're going to find a b to finally get to the destination. If we don't have any a's, then we can just directly go to destination through the b path. But if we have a's, then we can spend it all at the q state. So yeah, so that totally works. Yeah, so to actually think about the other repetition case we have, which is the plus, which is a plus operator. I want you guys to think about how we can actually create a maze for a plus b, and I will encourage you guys to think about it in the way to by trying to modify this particular diagram for a star b, without trying to think of any other like special constructions just to make a plus work, because there's a pretty easy way to just modify it. I guess a more specific question would be, how can we rewrite this plus operator, or rewrite this regular expression so that it doesn't have a plus operator anymore. We know that plus is 1 or more, while the asterisk is 0 or more. So maybe there's a way for us to get rid of the a and use, or to get rid of the plus and use an asterisk instead. Ah, frig. Well, unfortunately, I just accidentally showed it, but well, here it is. So we know that a plus b is really the same thing as a, and then a star b. So so yeah, a plus is 1 or more, a is exactly 1a, and a star is 0 or more a. So combined together, it's it's going to be 1 or more. So if we just want to translate that directly into the finite state automaton, that totally works. So we first have to get into an intermediate state by giving out an a, and then the intermediate state has a self loop with an a, which expends all the rest of the a's that we have, and finally we get to the final state with a b. So if we have a b, then we can get from q to intermediate, then to b. But if we only have b, then we can't get into the intermediate state in the first place. So yeah, so this is going to be the last slide on these finite state automaton things. Are there any questions on this type of material? So Evan John says, how does the star prevent overconsumption? Like, say, if we have dot star and then a. So so I don't really have a super good answer to your question, but we can think of it this way. So let's just say that the mouse is quite cunning in that it knows exactly which path to take, even at the very beginning. So for example, if we have 15 A's, or 15 A's exactly, then by the end of the 14th A, the mouse will be quite cunning and look at what A's we have in the very end, and if we only have one A in the left in the list of characters that the mouse has, then in that case it's going to get to the final state. This is also a point where I like to point out that there are some differences amongst the different flavors of regular expressions I talked about earlier. So what I'm trying to do right now is basically like using the POSIX BRE and ERE flavors. So only those things we know can actually be translated into finite state automata. If you use the Perl-inspired ones like JavaScript or some other ones, then there are some features that they provide that cannot be translated into a finite state automata. And I also talked about how we can control how either eager or lazy the mouse is. And in fact, there are flavors out there that allow you to control this, whether it's lazy or eager. And yeah, in fact, those flavors can also be translated into finite state automata, assuming they don't have any of the forbidden features. So yeah, I know this is not super satisfactory, but we can, just for the purpose of the analogy here, let's just say that the mouse is quite smart when choosing which path to take. And it's also not too difficult to think of what we can do with other constructions in regular expressions. For example, if we have a dot, then we can just have a special type of arrow that says, you can give me any character, and then I'll let you through. So that'll work. If we have, for example, the brace syntax we talked about earlier, for example, if you have like brace 2, then we can just add more locations, so we can expand that out to like A, right? And if you have like 4 or more, then we can have 4 of these A's, and then a self loop back into itself for the remaining infinite A's that we can have. So yeah, so those you can, the best way to think about these things is try to reduce these more concise syntax to something that we already know how to do. And we already know how to do like the asterisk and the plus, and that actually gives us a lot of ability to reduce the other features of regular expressions into. Anyway, I hope that was a fun little introduction to finite state automata. But I want to connect that to back to the theoretical computer science thing I was talking about earlier. So basically, what people ended up finding out was that in 1959, Ravi and Scott proved that modern computers can be very efficient in finding cheese in these mazes. And as I mentioned earlier, sometimes the mouse has to look a bit into the future to see which path, to see how these two paths differ. And in those cases, they're going to decide with which path to take. So apparently, there is a way to make our computers just as smart as the mice in deciding the cheese. And yeah, so in more detail, they are able to convert all of these mazes that we just created into a more restricted form of the mazes called deterministic finite automaton. And that we have known for a long time to be quite efficient. And yeah. So they proved this as a result, and in the 70s they got a Turing Award for this particular discovery. And as we know, the Turing Award is in fact the top prize or the highest prize in computer science. So that just shows how important this discovery was to the entire field of computer science. And just as a very last note, if you're interested in learning more about this topic of automata and such, you can consider taking CS 181, which is about automata theory and other such things. In particular, if you're a computer science, or I believe computer science and engineering as well, you'll be required to take this class anyway. So yeah. But if you're not CS or CSE, then you can definitely take the class as an elective if you have such a CS classes. But yeah, so before we end this workshop today, we have a Kahoot for you guys actually. So so let me start the Kahoot quiz. I'm going to stop sharing real quick so I don't accidentally leak the list of questions. But yeah, stay right here, and I will create this quiz. Okay, cool. Let me share again. Let's go with share screen. Aha, there we go. So the code will be 8133995, and you can join by going to kahoot.it. Just as a very last note before we get too much into the Kahoot, please remember to fill out this feedback form for us. Yeah, so again, this is the very last session of tooling series for this quarter, and so for all of you guys who have been coming to our workshops, we really hope that you've learned something, and please fill this out so we know how we can provide better workshops in the future. Except for those who are graduating. Sorry, Elena.
Tim, would you like me to stop the recording?
Yeah, sure.